A reminder that Quiz 2 is coming up in 2 weeks. It's a take-home exam, and you have to be in lecture 2 weeks today, so Wednesday, so that we can tell you what the rules are in no collaboration for the quiz. Today we're going to talk about more graph algorithms and something called shortest paths. Okay, shortest paths is a very natural problem. I want to get from here to over there using the shortest route. People plan shortest paths all the time. When you walk to school or to home or wherever, or take the T, I mean, all of these things can be phrased as shortest path problems. Okay, so it's about time you knew how to do it algorithmically. Okay, so the phrasing is you have some digraph, some directed graph. Let's call it G. It has vertex set V, edge set E, okay, usual setup. But in addition, we have edge weights. So for every edge E, we have a weight W of E associated with that edge. Okay, so we call that the edge weight function. And in general, it takes some edge in the set E, and it maps it to a real number. Okay? Any real number, although mostly we'll be thinking about integers because they're a lot easier to represent. Okay? So let's do a simple example. I guess I should talk about paths first. Okay, so suppose we have a path in the graph. Okay, so here's a path. Okay. Each of these edges in the path has a weight associated with it. So let's say we have 4, minus 2, minus 5, and 1. Notice the weights can be negative. Okay, they could be 0, positive, whatever. Then if I have this path P, I call the weight of the path W of P to be the sum of the weights of those edges. So if my sequence of vertices is V1, V2 up to Vk, I want to add up the weights of the edges from Vi to Vi plus 1 for all I. And you'll remember that this is somewhat of an abusive notation, because parentheses Vi comma Vi plus 1 end parentheses is an edge. W is a function. I should, in principle, have another set of parentheses around this, but that makes it messier. We understand what that means, so we're allowed to abuse notation, right? So what's the weight of this path? Who can add? Someone add for me. 2? Cheat. Negative 2. Thank you. Okay, just adding up these numbers. All right, so this is sort of, you think of this as the length of the path. Okay, but it's weighted by each of the edge weights. And now we'd like the shortest path. So why don't I go so what's the shortest path? Shortest path is just the path with the least weight. Okay, that's easy enough. So more precisely, the shortest path from U to V, for two vertices U and V, is a path from U to V with minimum weight. So out of all the paths from U to V, we take the one with the smallest weight. And in particular, the shortest path weight from U to V. Okay, so there may be several paths of shortest weight, but they all have the same weight, namely the shortest one. Okay, so we're going to use some notation throughout this lecture. There's delta of UV. That's the minimum weight over all paths from U to V. Okay. And one special case is it may be that there's no path from U to V. And so in particular, there's no shortest path. Okay, so in that case, we say that delta of UV is infinity, because it takes an infinite amount of time to get from U to V, because you just can't get there. Okay, if there's no directed path from U to V, then we define delta of UV to be infinity. And otherwise, it's some number, non-infinite number. Okay. Now we want to solve the shortest path problem. Okay, we want a good algorithm for finding shortest paths. If I give you a graph and I give you a weight function and I give you U and V, two vertices, I'd like to know the shortest path from U to V. Okay, that's sort of the simplest formulation of the shortest path problem. So what's sort of the most naive thing you could do to solve shortest paths? I mean, what's sort of like the most brain-dead thing? Yeah. Try all the different paths. Yeah, I mean, to just implement this definition, right? It says, look at every path from U to V. There's a lot of them. You can figure it out. It's exponential. Just compute each of their weights. That's easy. It takes linear time for each one. Take them in. Okay, so that's the starting point. It takes exponential time. So it's not a good starting point, but it gives you a feel. At least you can solve this problem. There are some problems that there's no algorithms for. Okay, at least there's an algorithm, which probably doesn't surprise you. And today we'll look at good algorithms. Okay. What's maybe a more clever way to go about this? What techniques could we use? Okay, don't think of an algorithm. Just think what techniques are applicable to this sort of problem. There are a lot. We've seen a few techniques lately that are really powerful and apply to this problem. Any guesses? What have we seen lately? Good techniques for solving problems. Okay, there's usually one right answer to this question. I mean, there's usually one answer that always works to this question. Yeah? Dynamic programming, right. Dynamic programming is so powerful, it'll solve just about anything. Okay, anything you can solve in polynomial time. So you can do it here. Okay, what do we need for dynamic programming? Yeah. Optimal substructure, right? You just handed in problem set 8. You know all about optimal substructure. Okay. Well, does anyone have an idea of what the optimal substructure is with shortest paths? I want to show that there are shortest paths within shortest paths, something like that. Yeah?
Given a vertex W such that W is on the path from some path from U to V, if the path U, W, and then to V is optimal, then each of its components U to W and W to V must be optimal, otherwise standard contradiction.
Okay, that was a little longer than I was expecting, because that included a proof. So I think the essence of what you're saying is if you have a shortest path from U to V, and there's some vertex in the middle, then like from U to that vertex in the middle is also shortest. That's one thing you said, right? Okay, so so another way to say that is if you have any shortest path, and you take any subpath of that shortest path, that's also a shortest path. Okay, so the picture is we have some path from, let's say, U to V. And let's say we take some subpath. Let's say we start at X and Y. Okay, there's a subpath. Because X and Y are along this path from U to V, there's a subpath from X to Y. Okay? And the claim is that that path is also a shortest path from X to Y. Why? Okay, you gave one proof. What's a very short proof to this lemma? Yeah. Otherwise, we substitute that path as a shorter one. What's that technique called? Cut and paste. I won't give you the hint. Right. I know that I'm assuming that from U to V is the shortest path from U to V. If this path from X to Y were not a shortest path from X to Y, there's some other path that goes along here from X to Y that's shorter than this one. And so if I cut this part out and substitute that path in, the path from U to V gets shorter. And that's a contradiction because I assume the path from U to V was shortest. Okay? So that's easy. So now we have optimal substructure, which is great. We'll use this property. But we won't end up using dynamic programming. Okay? It turns out there's an easier thing that we can do. What's the easier thing that we can do? Okay, we've seen this before. Greedy. Yeah. So it turns out there's some really good greedy algorithms for the shortest paths. Okay, we'll see one today. But first I want to tell you another property about shortest paths, which is the triangle inequality. How many people know the triangle inequality? About half? Okay. Everyone should know it, right? If you've seen the definition of a metric or whatever, it comes up all over the place. The property is, suppose I have three vertices, U, V, and X. Why do I call them U, V, and X and not U, V, and W? It's sort of pedagogical. Yeah? Because I don't confuse U next to V as the W. No. That's reasonable, but yeah. W is the weight, right? W is my weight function. I'll always use W to mean the weight function. So don't use W when you're talking about weighted graphs, because then you'll get confused, and we'll get confused when we grade it. Okay, so what's the picture here? Have some vertices U and V, and there's some shortest path between U and V. And I'm interested in some intermediate node X, and there's some shortest path from U to X and some shortest path from X to V. And, well, the claim is obvious. So I should say what the claim is. So the shortest path from U to V is at most the shortest path from U to X plus the shortest path from X to V. Okay, because one way to get from U to V is to go the shortest way to X and then the shortest way to V. Okay, so in particular, this is a path from U to V, and so the shortest path can only be shorter. Okay, so that was the proof. U to x to v is one way to get from u to v. Okay, so that's, if you're familiar with the term metric, this just tells you that delta is a metric. The shortest paths form a metric. Okay, that's good. That's a useful property. We'll use it again. Okay, getting closer. Eventually we'll get to algorithms. But we need to understand shortest paths a little more. Okay, so more properties. We have a new eraser today. Never had this eraser before. It's reasonable, but not the greatest. Next question, sort of general understanding. When isn't there a shortest path? Okay, so what situations might we not have a shortest path from u to v? Yeah. When there's no path from u to v at all, right? So that's when it's disconnected. Exactly. So that's the situation I've already mentioned. Is there any other situation where we don't have a shortest path from u to v? Yeah?
Maybe when there's two equal length paths?
When there's two equal length paths. Okay, that's a good answer. Then there's no the shortest path, but there is a shortest path. In fact, there's two. Okay, so that I count as okay, but that's a good point. Yeah? If you have infinitely many nodes, that's on the right track. But let's say that the graph is finite. Could it be that my shortest path has infinitely many nodes, even though the graph is finite? Yeah. If u and v are the same point, yeah, that is a particular case. But normally you'd think the shortest path from u to u is 0. Okay, so that counts as a path, yeah. When you have a loop, yeah, that's getting on the right track. So what about the loop? I mean, if I go around a loop many times, my weight gets longer, right? Yeah. If the weights are negative on the loop, right. If I have a negative weight cycle, the more times I go around it, the shorter my path gets. Okay, this is rather counterintuitive. Okay, but this is something you need to know about. Okay, if G has a cycle whose total weight is negative, okay, so it's a negative weight cycle, then some shortest paths don't exist. So the picture we have in mind is you want to go from some vertex u to some vertex v, and along the way you encounter a cycle that you can follow. Where it has negative weight. It's an abbreviation for negative weight. So if every time I go around this, the weight of my path goes down by at least some amount, then if I want the shortest path, the lowest weight path from u to v, I should go around that cycle as many times as I can afford to. Okay? It doesn't cost me anything. In fact, it gives me money every time I go around the cycle. Right? So I get smaller and smaller weight. Actually, I never finish. There's no shortest path, because any path you choose that goes around k times, well, if I went around one more time, k plus 1 times, it would be even shorter. Okay, so there's no one shortest path. It's kind of annoying, but that's the way it is. So we'll say that delta of uv is negative infinity. Okay, because there's sort of a negative infinite weight path. All right. That's something we'll need to deal with. But if we have no negative weight cycles, then in particular, the shortest path is defined as long as the graph is connected. Okay, strongly connected. If it's disconnected from u to v, well, then we'll figure out that the weight is infinite. Sorry, the shortest path is infinite length. Okay. I'm going to want the triangle inequality. So I'm going to give you now a slightly different formulation of the shortest path problem. Okay, this is called the single source shortest path problem. That's what we're going to solve next. And the goal is you're given some graph, and you're given some weight function, and you're given a source vertex v. Actually, S. S for source. And the goal is to find a shortest path from S to every other vertex. Okay. I'll make the problem a little bit easier and say I don't actually want to find shortest paths. I just want to find the shortest path weights, okay, which are delta S comma V for all vertices V. Okay, so instead of just given u and v, finding one shortest path weight, I want to find n of them, okay, where n is the number of vertices. I want to find v of them. And as you mentioned already, we're going to use a greedy algorithm. Okay, and this algorithm is called Dijkstra's algorithm. Okay, it's named after Dijkstra, who came up with it a long time ago, right? When did he? Does anyone know when Dijkstra's algorithm was? It's like early 60s. Okay. 62, 63. Good.
But it's actually a lot earlier than that. Rivka,
Ah.
I think in the 30s.
So it shouldn't be called Dijkstra's algorithm.
Well,
Oh, Rivka. All right. Dijkstra really called it an algorithm.
really Dijkstra.
Yeah. Okay. I mean, yeah, people use this all the time. Okay, but everyone calls it Dijkstra. Good. We're going to use a greedy algorithm. So here's what we're going to do. There's going to be three main steps or ideas or whatever. We're going to assume that at any point in time, we have some set of vertices where we know the shortest path from S to V. Okay, in the font I'm using, big S and little s look rather similar. So to be clear, this is big S, this is little s. Okay, well, how do we get started? What shortest path distance do we know from the very beginning? Okay, from S to some other vertex. It's almost too easy. It's so easy you don't even realize that you know it. What do we know? Itself, yeah, from S to S. Initially, we know the distance from S to S is 0. Okay, so that's how we'll get started. Initially, the set S will just be little s. Okay? Let's see, what else do I want? That was the first step. Second thing we'll do is try to grow S. We want to know the shortest paths to more vertices. So at every step of the algorithm, this is the main loop, we'll add to our set S a greedy choice. So we're going to pick some vertex that's not in our set S, and we'll claim that we already know the distance to it, and we'll do that greedily. So all the time, we're going to be maintaining distance estimates from S to some vertex. So this little s, the source S. And I'm going to pick the one that has smallest distance estimate. So this is a greedy choice. And I claim that that vertex, that distance estimate is actually the distance. Okay, it's actually the shortest path weight. That's what I mean by distance. And now we have to maintain these distance estimates. So it turns out, so I'm going to show you the code in a moment. It turns out that we don't have to update all the distance estimates. We just have to do it for the vertices that are adjacent to the one we picked. Sorry, not S. S is the source. I'll update the vertices adjacent to V, the one that I picked in step 2. Okay, and then I'll repeat. That's the algorithm. And so go here. I should mention one other thing, which is that this algorithm assumes that we don't have negative weight cycles. Okay, in fact, I'm going to assume for now, and for the rest of the lecture, that there are not even negative weight edges. So the weight of any edge UV is at least 0. Okay, so in particular, the shortest path weight from U to V is strictly greater than negative infinity. Okay, so we don't have this case. Rule that out. Going to be able to fit it here? Probably not. All right, this is an unfortunate board choice. I want to keep up the triangle inequality. Okay, but I also want to use that board. So let me copy it. Okay, so here's the algorithm. So we're given some graph G, we're given a weight function W, we're given a source vertex S. We want to find all the shortest paths from S to every other vertex. Okay, and initially, as we said, the shortest path, the distance to S from S is 0. Okay, so in general, D bracket U is, let's say, the distance delta from S to U if U is in our set S, and otherwise it's a distance estimate. Okay, and initially, as I said, actually, I'm not even going to worry at this point. Okay, I'll set S initially to 0. Okay, I'll just claim that I don't know any distances. And we'll choose this one in a moment. In general, d bracket u is the estimate of our current estimate of the distance from S to u. Okay, we'll use that variable a lot. We have to also finish initializing d. Okay, so say for every other vertex in V minus the source, I will set the estimated distance from S to V to be infinite, okay? Because I don't even know whether it's connected. So let's just be rough and say you can't even get there. Okay, and we'll improve those distance estimates as we go through the algorithm. Okay, in addition, have a variable q, which is a priority queue. It's a priority queue of vertices. So initially, it's going to be the entire set V, the entire set of vertices. And in general, it's V minus S. Okay, remember, S is the set of vertices whose distances we know. Okay, and their distance is d bracket u. Initially, I don't know any distances, I'm saying. And so this is sort of the vertices left to process. I've got to process all of them. Right. Let me just write up the rest of the algorithm. So that's it. Basically, I'm executing these two steps, 2 and 3. I've already done 1. It says, at each step, we're going to add to S the vertex whose distance estimate from S is minimal. Okay, so I called it V up there, and I'm calling it U here. I just take, so the priority queue, I should mention, the priority queue it has to have some keys to sort on. Okay, the priorities, or the keys, is given by this function d, okay, this variable d. D tells me for every vertex a distance estimate. So extract min of q is telling me the vertex that has the smallest distance estimate. Okay, that's part 2. Then part 3 is we need to update. Part 3 is we need to update distance estimates. Okay, and that's this for loop. And we're supposed to update the distance estimate for every vertex v that's adjacent to u. Okay? And this is what we do. Can anyone tell me succinctly what's going on here? What am I trying to do here? Yeah? Take the minimum of the current distance, like the current distance estimate, and the distance from u, or by way of u. Right, so we know now how to get to u. What this line says, if I add u to s, that means I now know the shortest path to u. So I'm checking, is it shortest to go to v by way of u? Should I go to u? Should I go to u? That takes d of u weight. And then go from u to v, because there's an edge from u to v. Okay? So this is taking the min of that and what my old distance estimate is. So that's natural enough. Okay, this is sort of the obvious algorithm. But can you tell me another reason why we're doing this? What effect this has? Something else on the board. Yeah? It's changing the priority queue. Okay, that's a good point. That's not what I had in mind, but I have to mention that also. So this is an implicit call to decrease key. Okay, whenever I change D, that's changing the key in the priority queue, so I have to call decrease key on the priority queue. Good. Anything else on the board that's relevant? Yeah?
It then enforces the greedy property on the
Enforces the greedy property. Close. I had in mind a different property. The triangle inequality. Thank you. This thing. Just textually, this looks like the triangle inequality. Okay? So we're fixing. See, the thing is, if we just left dv how it was, then dv, which is the distance estimate from S to V, would be larger than the sum of these two distance estimates. Okay? And you can write that exactly in this form. And if we just left d of v how it was, then the triangle inequality wouldn't hold. And that's wrong, because it better hold if we're going to find delta. Okay, so this is sort of like fixing the triangle inequality. Okay, so this is called a relaxation. So we say that we relaxed the edge uv because intuitively we have this constraint. We've got to satisfy this property if we're going to find the right delta function. Okay, and we're relaxing that constraint. Now we don't have to worry about it. Okay, we're fixing it. So let's do an example. I'm going to need some space here. So leave some room up here. So here's a weighted graph. And here's my Q. Okay, so initially I set my Q to be the entire set of vertices. Okay, so every vertex is in here, and the keys of those vertices in that Q are given initially by those lines up there. So d of s, I should say what the source is. So let's say we want to compute all the distances from A. Okay, then we know, first thing we do is set d of s to 0. So d of A is 0. And the other ones are all infinite. Okay, that's the beginning. And now we're going to do this loop. So we're starting from A. So we set the distance from A to A to be 0. Now, out of all of these vertices, I'm going to pick the one that has smallest weight. Okay, that's the extract min. 0 is a lot smaller than infinity, so I'll pick this guy. Right, now I add. So I should also keep track of my set S. Initially, S is empty. Okay, but the first thing I do is I pick out A and say, well, A has the smallest weight. It's 0. So I'll add A to my set S. Okay? And I'll also remove it from the priority queue. So it's gone. And the other thing I want to do is part 3. I want to update these distance estimates. So I look at all the outgoing edges. So that this notation, V is in the adjacency list of U. Okay, so V is a neighbor of U. coming from U to V. So there's an edge UV. Okay. So there are two edges starting at A. There's one that goes to B, and there's one that goes to C. Currently, my distance is 0. It doesn't take me anything to get to A. And the distance here is infinite. The distance here is infinite. So all of these have infinities on them. So I'll label them. Move this out of the way. Okay, well, infinity is greater than 10, and infinity is greater than 3. So I'm going to update these to 10 and to 3. Okay, and I'll do that over here, too. So B now has distance estimate 10. C now has distance estimate 3, because there's a path from A to C that has cost 3, and there's a path from A to B that has cost 10. Okay, not very exciting yet. Now we get to do a little bit of work. We say, well, which of these numbers is smallest? Okay, before it was 0. Now 3 is the smallest. 3 corresponds to vertex C. So I go to vertex C. I add it to my set S. Of course, I've run out of space for my set S. So, I don't know. Let's say these are the vertices in set S. So initially A is added to set S, and then C is added to set S. Okay, now I have to update the distances. So from C, I can immediately get to B by this edge, and I can get to E by this edge. Okay, if I go to B this way, I have a cost of 3, which is how long it takes to get to C, plus the cost to B. So that's 4. Add them up, that's 7. 7 is smaller than 10, so that's a better route. So update that distance to 7. Okay, I can also get to E by a cost of 3 plus a cost of 2, 5, which is better than infinity. So update that one too. Okay. So now B has a cost of 7, E has a cost of 5, and D we haven't changed. Okay, so my priority queue now has 3 elements, and the smallest element here is 5. That corresponds to vertex E. So I take my vertex E. I say, OK, now it's in my set S. I claim that 5 is the true distance from A to E. And I look at the outgoing edges. There's one edge from E to B. Right? And I say, OK, that has cost 9, that edge. It took me 5 to get here. I add those up. That gives me 14. So the distance to D is now 14. What should I do next? Sorry? Take the smallest vertex, which is 7, which is B. Good. I take B. I say, OK, it's distance 7. I claim that's the shortest distance from A to B. And I will update all the outgoing edges. So there's one edge goes from B to C. We can check it. I already did C, so it better not be shorter. I claim that I've already added C to S. But let's check. It took me 7 to get here, and then 1 to get back, so that's 8. 8 is bigger than 3. Okay, so that's no good. In fact, the path corresponds to going from A to C, up to B, and back down again, which is clearly the wrong thing to do. OK, the other outgoing edge from B is from B to D. That has a cost of 2. It took me 7 to get to B, and then an extra 2. That cost me 9. That's better than 14. So I'm going to update that to 9. OK, now my priority queue just has one guy. I extract them in, which is D. And I claim that S is now complete. I have the shortest distances from A to every other vertex. From A to C costs 3. From A to B costs 7. From A to D costs 9. From A to E costs 5. OK, that gives me the weights. You can pretty easily also from this extract the paths, all the shortest paths. Yeah, question? Yes. Good. Thank you. So I just finished with D, and then I said I was done. But in fact, the algorithm goes through and says, well, is D a good way to get to other nodes? Okay, so there's one outgoing edge. I should check that 9 plus 7 is smaller than 5. Okay, good. That's the very end of the algorithm. It's not going to find anything because I claim I already had the shortest path to E. But the algorithm does check it, just for good measure or whatever, because it doesn't know any better. It doesn't want to have to check whether things are in S. So is this clear? Is it totally obvious that this algorithm it works? It finds the shortest paths? Is it not obvious to some of you? One person? So this seems clear, I guess. It's greedy. Trouble is, greedy doesn't always do the right thing. Okay? It's sort of always taking the thing that you can get to fastest, but it's not clear that that's the right thing to do. Okay, so I'm going to prove correctness. And it's going to take a long time. It's not an easy proof. And to me, it's not obvious that this works. Maybe you have a better intuition than I do. It feels like the right thing to do. Okay? I think it's obvious that this is a candidate solution. But it's not obvious that this is the solution, that this really finds the shortest paths. So I'm going to prove correctness. Part 1 will be, I'm going to prove correctness in 2 parts. The first part is actually an invariant. It says that my distance estimate from S to V, that's D of V, is at least the shortest distance from S to V for all V and for all time. Okay, so I claim that at all times during my algorithm, this invariant holds. Okay, maybe starting here. Okay, at the very beginning, I haven't set V. I haven't set D. Once I've initialized D, so I should be precise, after initializing D. I claim that my distance estimate is no smaller than the shortest distance, which better be true if I'm going to find the shortest distance. Okay, any proofs? Why is this true? This is the easy half. The second half is hard. Yeah?
Because when we're keeping the distance, we have path and how we can get there. So this path.
Right. When we update the distance, we have in mind a particular path to get there. Right. And if we have a particular path, that path has to be at least the shortest path. Okay, so I'm not going to write down, I don't think I have time to write down the formal proof, so I'll just give the sketch. Okay, it's more important to spend time on the second half, so I'm going to do that. The sketch is that D of U is set only when a valid path of that length has been found. Okay, namely, we assume by induction that we've already found a path from S to U of this cost. And now if we take that path and extend it with the edge UV, that's a path from S to V. So I really have a path in mind here that first goes to U using whatever we've already computed, and then adds the edge UV and gets to V. Okay, you should read the proof in the text or on the online notes, because it's more formal. But I want to go on to the second part of correctness. All right. So this correctness part 1 said, I don't find any paths that are even shorter than shortest. Okay, that's sort of obvious. The hard part is that this algorithm, Dijkstra's algorithm, actually finds the shortest path. Okay, nothing longer. It's pretty clear it's nothing shorter. And this is not an invariant, it's just a termination condition. Okay, because it won't be true that we have the shortest path until we're done with the algorithm, obviously. So when the algorithm terminates, we have that d of v equals the shortest path cost, or the shortest path weight from S to V for all v. Sorry, I'm misspelling Dijkstra. All right. So let me give you the setup. The first thing to observe is that when you add a vertex to the set S, its cost no longer changes. Okay, we removed it from the priority queue. When we added B to S, we said, OK, its cost is 7. We're not going to change it from now on. So d of v doesn't change once v is added to S. Okay, so if we want to show that at the end of the algorithm d of v equals something, it's enough to show that when v is added to S, this property holds. D of v is equal to that particular thing. Instead of looking at the very end of the algorithm, we can look at this time when v is added to S. So for all v, d of v equals what we want, the shortest path cost from S to v at the time when v is added to S. Okay, so that's our goal. So let's suppose that this isn't true. So we'll do proof by contradiction. Let's suppose that there's a shorter path than this. Okay, that this cost is smaller than this cost. Okay, we know that it's not larger. So let's say that P is the shortest path, or P is a shortest path. So in particular, the weight of that path is equal to this delta, the optimal distance. And let's suppose that that distance is smaller. Okay, so suppose that W of P, which is delta from from S to U, is strictly smaller than d of v. Okay, for contradiction. And here's what I'm going to do. I should draw the picture first. So we have some path from u to v. Let's say u is here. Sorry, from s to u. Get my variables right. So we have a path from s, ends at u. Okay, and let's imagine this is my graph, G. And in particular, some of the vertices of G are currently in my set S. All right, maybe, so I need to be a little bit more precise. I left out a line. That would explain it. Sorry. What the hell is U? You guys are supposed to bug me when I'm doing something wrong. What's U? I didn't say what U is. Oh. I'll sneak in a line here and then repeat what I said so you have time to copy it if you want. Okay, so what is U? So I'm going to say U is not just any vertex that has the wrong distance, but it's the first one. So we're going to say it's the first vertex about to be added to S. So it hasn't quite been added yet. So I'm at the line, I'm at this line right here. I haven't quite executed this line, so I'm about to add S to U. But let's suppose that that was the wrong thing to do. I shouldn't add U to S because the distance estimate from S to U does not equal the shortest path distance. Okay, sorry about that. So let's go through the proof argument again. We say all we care about is that d of v equals delta of SV when we add v to S. Okay, so let's suppose that when we add a vertex u to S, we don't have that property. Okay, d of u does not equal the shortest path distance from S to u. Okay, then we'll get a contradiction. Okay, and so we'll say, well, if that's not the shortest path, let's see what the shortest path is. So let's just say P is the shortest path from S to U. Okay, so the way to that path is delta of S of U. And this is no longer a supposition, because we already supposed that the weight of the shortest path is strictly smaller than the distance estimate. Okay, so the distance estimate is wrong. We want to get a contradiction and prove that, in fact, the distance estimate is right. Okay, so we have some path P. Okay, it goes all the way through the graph and does all sorts of great things. Now, some of the vertices in here, so this is visiting lots of vertices along the way, conceivably. So this is my path P. This is the shortest path from S to U, or a shortest path. Some of these vertices that I visit are in my set S, and some aren't. Okay, so let's say these ones are in my set big S. Okay, I know that that little s is in my set, and I know that U isn't in my set. I was just about to add it, but I haven't finished yet. Okay, so some of these vertices along here are in S, some of them are not. And I might go out of S and come back in S, but I start inside S and I finish outside S. Okay, so out here is V minus S. So at some point I cross. Okay, let's look at the first time you cross this boundary. I go from a vertex X that's inside S, and I go to a vertex Y that's outside S. That's what I want to do. So consider the first place that the path P exits the set S, say along an edge xy. Okay, so y is the first time that I leave S and get to V minus S, and x is the guy right before that. Okay? Well, what do we know? I claim, first of all, that d of x is delta of Sx. Why is that? I claim that my distance estimate from S to x is the correct one. It's exactly the shortest distance from S to x. So why do I know that? Yeah. Because P is the shortest path. Yeah. Good. P is the shortest path. Actually, I'm not talking about P here. So that's not quite right. You're right that this path, the subpath from S to X, is the shortest path because of optimal substructure, right? So we know that. But I want to show something about the distance estimate. So that's not quite it. Yeah? Because X is already in the set S, right? Because X is already in the set S. And furthermore, I chose U to be the first vertex that gets added to S that has the wrong estimate. Okay, so if I've already added X to S, I know that it has the correct estimate. Okay? And because U was chosen to be first. Okay, so that means X came earlier on, and so it has the right distance estimate. What else do I know? So let's consider the time when X was added to S. Well, when we added X to S, we did part 3 of the algorithm. We looked at all the neighbors of vertex X. In particular, a neighbor is Y. And we relaxed all those edges. So in particular, we relaxed the edge XY. Okay, that's what the algorithm does. So it checks whether my new way to get from S to X, which is the optimal way, and then we add on the edge Y, whether that's a shorter path than whatever other estimate we had for getting to Y. Okay? And I claim that that is really the shortest way to get to Y. This is not true in general, but I claim in all this setup that I've given you, it is true. And my question to you is, why? So I claim that we set our new, at this moment when we relax the edge, the if condition is true, and we set the distance estimate of Y to this new path, the shortest path from S to X, which we just figured out. Okay, that's d of X. And adding on the edge from X to Y, and I claim that that's the shortest distance from S to Y. And the question is, why? No pun intended. Yeah? Because the optimal substructure, right. Because we know that this path from S all the way to U is a shortest path. And so in particular, from S to Y is also a shortest path, right? Okay, that's the point that you were making. Okay? So we know that this path is the shortest path, so in particular it goes through X. So we know that this condition holds. All right. So I'll say because subpaths of shortest paths are shortest paths. Okay, that's a lemma that we proved earlier. We're almost done. Still want to find a contradiction. But I'm starting to learn things about X and Y. And we'll see why we care about X and Y in a moment. Okay. So I claim, then, that d of Y equal to delta of Sy is at most delta of Su, which is at most du. Okay, why is this true? Well, I just said that. Okay, I just proved to you delta of sy is equal to d of y. Okay, so this is the previous line. Why is this true? Yep. Triangle inequality. Yeah, okay. Sorry. Yeah. So you can go from s to x, sorry, s to y, and then from y to u. And the triangle inequality that says going from all the way from s to u is no longer than going from s to y and then from y to u. Okay, and that, actually, that's not quite enough. But it's, yeah. Because you have positive weights, and because s to y is a subpath of s to u. Okay, so this is because we have a subpath, and because we have positive weights. Good. So this is where we're using positive weights. And why is this true? Yeah. Because the first thing we proved, right. This is the first part of correctness. Part 1. We showed that if we have a distance estimate, it's no worse, sorry, it's no better than the optimal, which is the intuitive thing. Why do we care? Do we get a contradiction? So do we have something else here that might be useful? We said d of u did not equal delta of su. And in fact, we know that d of u can only be bigger. Right? That's, again, correctness part 1. So we know that d of u is bigger than or equal to delta of su. And here we're saying, all right, is that what I want? That's not quite what I want, sorry. What I want is that d of u is less than or equal to d of y. Okay, which is the opposite way around. Here I'm saying d of y is less than or equal to d of u. But in fact, I claim that d of u is less than or equal to d of y. Why is that? You have to go way back to the beginning of the proof. Yeah. Because u is the first vertex to be added. That's not quite it. It's the way that we chose u. Right? In the algorithm chooses u by extracting the minimum from the q. So that means that it has minimum d value at this moment. Okay, so d of u has to be smaller than or equal to d of y because we chose u, not y. Both u and y are in the set v minus s. And so they're in the priority queue. We chose the guy with minimum value, with minimum key. Okay, because u was chosen to have minimum d value. Okay, so that means if we know that d of y is less than or equal to and larger than or equal to d of u, that means that d of y equals d of u. We're nearly done. Because we know that this is correct. We know this is delta of sy. Okay, we prove that here. And d of u, let's see, what else do we know? So in fact, maybe I should rewrite this a little. That's true. We know even more. Right, we have this whole inequality chain from d of y all the way to d of u. And we're saying that, in fact, it turns around. So it can go the other way. So I can just copy this line, but with equalities. Because I know that this thing on this side is equal to this thing on this side. I know that all of these things are equal. Okay, that's what I really want. This is a tricky proof. Does anyone see the contradiction? Yep. Go ahead. Either one. Right. We assume that du was not equal to delta of SU. Okay, it was strictly greater than. And that's the end of the proof. Whew. Okay, this is not easy. I got through it because I have my cheat sheet. Okay, what's going on? We're saying we claim that d of v when we're done is equal to delta of SV, so that the distance estimate when we're done is equal to the shortest path distance. Okay? And what we said was we only care about the time when v was added to S. And so let's suppose that we add some vertex to S, but we had the wrong distance estimate. Okay, if it's wrong, that means there's a shorter path from S to U. So let's look at the shortest path from S to U, call it P. Then we have this picture. We say, well, I want to get a contradiction. I want to say I shouldn't have chose U. I should have chose some other vertex. Well, which vertex should I have chosen? Probably this guy, because this guy was just on the boundary from S. Okay, this guy was just out of what we knew. And in fact, you can see from the picture that getting from S to Y is cheaper than getting from S to U, right? Just because it's a shorter path. And so I should have first picked Y. And from the priority queue, this guy should have had smaller cost than U. So Dijkstra's algorithm would have chosen Y and then updated this cost first. But we assumed that U was first, not Y. Okay, that's basically what's going on. There's all this manipulation to get all those inequalities right. And because we might have equality, it might not be that Y is strictly shorter than U. It might be equal. Okay, so there was this mess. How long does this algorithm take? Any questions about the proof? Okay. What's the running time of this algorithm? How many times do I do the whole thing, the whole loop? How many times do I go through this while loop? Number of vertices, right. How many times do I go through the inner loop for each vertex? Sorry? The degree? Yeah. So exactly the degree of U times. Okay, so the running time, why don't I write it somewhere else? Is, well, for every vertex, I have to do an extract min. Okay, that's the dominant cost in the outer loop. I only do that once per vertex. And then, for the sum of the degrees time, I have to do a decrease key. Right, I had an implicit decrease key. The rest is just constant time. Okay, so if I have these two times, so I have some priority queue structure that does an extract min in some time and a decrease key in some time. How many times do I have to do the decrease key in total? V minus S? Not quite. It's not the number of vertices. It has to do with the degree. Yeah. Right, proportional to the number of edges. So I should put a big O around this. Okay, this is the handshaking lemma. Right? The sum of the degrees of the vertices is 2 times the number of edges. This running time should look very familiar. It's the same as the last algorithm you saw, Prim's algorithm for minimum spanning trees. Okay, and I don't have time to write what this gives you in terms of different priority queues, and because I have another thing that I want to cover. Okay, but in particular, you can get big O of E plus V log V. Okay, so that's a pretty fast algorithm. Number of edges plus, sort of like sorting the number of vertices. All right. And now, very quickly, I want to tell you about unweighted graphs. Okay, so Dijkstra's algorithm is cool. It's fast. But sometimes you can do even better. Okay, it's also correct. That's good. We like correct algorithms. It's very easy to come up with an incorrect, fast, shortest path algorithm. So let's suppose we don't have weights. In fact, the weight of every edge is 1. I claim then we can do better. Okay. So Dijkstra's algorithm becomes what's called breadth-first search. This is exactly what I wanted to mimic. Too bad. Okay, breadth-first search is also called BFS. Again, you give me a graph and some source. We know that the distance to S is 0. And we know that, well, we don't know much about the distance to any other vertex, so we set those to infinity. This is just like Dijkstra. Now we have a Q, which is initially S. And the key difference is that Q is no longer a priority queue. It's a FIFO queue, okay? A normal queue. First in, first out, okay? Things will just come out in the order that I put them in, instead of by priority. I'm going to forget about priorities. The claim is that that's OK. All I need to do is keep extracting vertices from this queue. So I dq, q. I get some vertex u. And then I check. I want to relax the edges. So I look for every edge from u to v. So for every vertex in the adjacency list of u, we say if. Now I just want to say, well, if I haven't even looked at v, if the distance to v is infinite from this line, then I'll update it. I say the distance of v is the distance of u plus 1. And I'm running out of lines. In addition, I add to the queue v. Okay, so the claim is that this acts just like Dijkstra. Okay, I initialize, then I say get the dq of q. I claim that that's the guy with minimum distance, with minimum priority. Okay, then I check if its neighbors have infinite distance. I'll update that distance and add it to the queue. So I claim that it's now an S. So the q represents, well, it's not quite S, so I won't write something down. It's a superset of S, subset of S. Okay. So I'm going to add v to q because I claim now v, we know the shortest distance. Okay. And I have a minute left. So I just want to show you an example. Because this is a really easy algorithm. We just made it look complicated because it's like Dijkstra. Or it's a little tricky to write down. But it's like the simplest graph traversal algorithm. Okay, and I'm just going to do this example until I run out of time, which is not very long. Okay, so this is the beginning of the graph. There's some other stuff which I won't get to. We start up here. Let's say that s equals a. First thing I do is initialize the distance at a to be 0. Okay, Brett's first search says, just look at all the neighbors of A. There's B and there's D. So initially my Q is just A, and then I remove it. Okay, and it has distance 0. Now I see, well, B and D are neighbors, so I'm going to add them to my Q and set their distances to 1, because I can get to A and 0, and then it just takes me one more edge. Okay? Now I take the first thing from my Q, that's B. I look at B. It has 2 outgoing edges, C and E. So I'm going to update their distances to 2, because it takes me 1 to get here and then 1 more. And I'll add them to the Q. They have cost 2. Okay? Then I go to D. Okay, notice D has the shortest, has the smallest value at this point, D value. Okay, and I look at the outgoing edges from D. I say, okay, I can get from D to E in 2, but that's no better. So I'm not going to change anything. In fact, I don't even care whether it's better. I just care that this is not infinite. Then I claim this has to be better. Okay, I'm not going to go through correctness. And I will stop there. But that's the algorithm. Okay, it's very simple. You just branch out. You go in levels from your vertex until you get all the distances right.